Hello and welcome back. Today is day 3 of inverse trig. Next class is our review period for test number 2. Go ahead and take a look at your syllabus calendar to figure out the window where you're going to take test number 2. Just to note that you hopefully have already finished quiz 6, that was last class, and that required forum number 2 is due midnight of whatever date you see there, with a thoughtful response due by midnight of class 25. Okay, number 1. We'll spend today solving a word problem and some complicated trig equations. All variables from today's class are in radians. If there's time left after doing the activity, spend it studying for the test. You'll find sample test problems at the end of this, well, it says at the end of this packet, but if you're taking the online class, you know where to find the sample test problems. Number 2, the pressure in a pipe oscillates 5 times an hour between a low of 90 pounds per square foot and a high of 230 pounds per square foot. Pressure at time t equals 0 is 90. At what times in the first hour will the pressure be 150 pounds? So we've seen all parts of this problem before except for the actual final part of this question. We have not answered any problems to date where we have a sinusoidal function and we're figuring out when something will happen. So we'll begin by drawing a good picture. So the pressure oscillates between 90 and 230. I'm not really worried too much about the scale. And at t equals 0, the pressure is 90. So we're going to start down here and at some point make it up to the top and then at some point make it back down to the bottom. And so we'll go ahead and draw one cycle here. And it says this oscillates 5 times per hour, which means that this thing right here must be 1/5 of an hour because we've got 5 of these in 1 hour. So you're welcome to put 1/5 of an hour. But the question here says what time, and it feels like not fractions of hours aren't going to be the natural way to write time. It feels like minutes are going to be the way to write the time. So we're going to let the units down here be minutes from, well, we'll just say minutes from t equals 0. And 1/5 of an hour is 12 minutes. So that's the first cycle, and then we have 4 more of these cycles here. So is that the right number? 1, 2, 3, 4, 1 more. And so ultimately here at the end of the 5th complete cycle should be 60 minutes into this process, and every bottom point here happens every 12 minutes. Okay, and this problem says at what times will the pressure be 150 pounds per square foot? So 150, again, don't really need to worry about the scale too much, but it's definitely above the middle, maybe because we have to find the middle anyway. Let's go ahead and write the middle. So the middle of 230 and 90. Let's see, what is that? 320 divided by 2, 160 is the middle. Did I say 150 was above? You can rewind if you want to, but 150 is below the middle. So we'll go ahead and draw our 150 in here, slightly below the middle. And we can see that that 150 hits this curve many, many times. And our job is to figure out exactly what times those, when that line hits the curve. Okay, so let's give this a shot. First thing we need to do is find an equation of this curve, which means finding amplitude and midline and all that stuff. So we'll go ahead and write in a few of these things here. Amplitude is the distance between the middle and the top. So 230 minus 160, what is that, 70? And we've already figured out the midline, which was y equals, what is it, 160. Okay, so that's fine. And then the other thing we needed was the period. Period in this case is 12 minutes. And we know then that well, we'll just leave it at that. And so then we'll start writing our equation. So our equation is normally a sine or cosine b factored out x minus, what do we call this guy here? We call it h, I don't remember. And then a plus k there. Okay, so let's start filling in the blanks. Y equals, okay, the A is the amplitude 70. So I said sine or cosine. Well, which one is it? In this case, we are starting at the bottom on the y-axis and then heading up. So that feels like a negative cosine. So how about we go ahead and make the change right here. And we're going to call this not just cosine, but negative cosine. So we got negative cosine of, okay, the b we're going to leave blank for just a second. X minus h, h is the horizontal shift. Well, if we call this a negative cosine, then we've saved ourselves some work. There is no horizontal shift. There are many other ways to write this thing with a horizontal shift, but for me, naturally, this is a negative cosine. Plus k, which was the midline, which was at 160. And the last piece of this puzzle was to find b, and remember that b is 2 pi on the period. So 2 pi over 12 minutes, which reduces to pi over 6. So that goes right in here. So that means that our final equation is y equals negative 70 cosine of pi over 6. I called it x. Maybe t is more appropriate because it's time. And then plus the 160. Okay, so I think that seems good. Maybe I'll go ahead and change the x's to t's back here to be consistent. Okay, and before moving on, I'd encourage you to check on your calculator. Make sure that the equation that we just came up with actually matches the scenario given in the problem. So how about we go into our y equals, and we'll go ahead and type in this function right here. Okay, and then how about a good window? Let's see. The bottom or the far left is at 0. Let's go ahead and look at all of these cycles here, which goes out to 60 minutes. We'll go by 12s. And then the bottom is 0 and the top is 230. So, and then maybe we'll go by 25s here. And let's just hit graph again, make sure you're in the right mode, which is radian mode. And that doesn't look promising there. And it's because I forgot my variable. Little details. Okay, so I called it t, but we'll call it x over here. And we'll try again. Okay, that looks good. It looks like it's starting right around 90, going up to the top of the window at 230. And we'll make sure we get 5 complete oscillations here in this space. So every 12 minutes, we can see an oscillation is finished. So that looks very good. And now I think we should move on. So it says we want the pressure to be 150. That's the value of either y or t. Which one is it? It's y. So we're going to stick a 150 on the left-hand side. Okay, and all of a sudden we have a full-blown trig equation that we're trying to solve, not just a formula for a graph, but a trig equation to be solved for t. And we spent the last couple of classes solving trig equations. So if you're feeling confident, then this is a good time to pause the video and see if you can find, forget about the solutions that are in this graph, but actually find all solutions. So don't forget that plus 2 pi k that we would stick on at the end. So pause the video here and come back when you feel like you've gotten to the final answer where it's t equals something plus something with pi's and k's in it. Okay, so if you're back and you haven't gotten very far, then you can just watch. If you've gotten pretty far, you might want to skip ahead in this video a couple of minutes. I'll try to go quickly through the process here. So first thing is to isolate the trig function, which is this piece. And that means subtracting the 160 and then dividing by the negative 70. So we'll do 2 steps in 1 here to save a little space. So subtract 160 gives me negative 10 on the left, and divide by negative 70, and that gives me 1/7. Okay, then we're going to take inverse cosine of both sides. And then we're going to use the calculator to get our first fundamental solution, and then we'll have to use symmetry to find the other one. So we're going to get pi over 6t equals something from the calculator, and then pi over 6t equals something else that we'll have to do work for. Okay, so what are we typing here? Inverse cosine of 1/7. All right, so 1.427. I'll write 4 digits. And then to find the other answer, we need to use the unit circle. Okay, 1.427 is in the first quadrant. Hopefully you see why that's true. Remember, it's pi over 2 at the top, so this is going to be pretty close to pi over 2, but it's still less. Type in pi over 2 on the calculator if you want the decimal. So right here is our 1.4, and this problem involved cosine, so that's related to the x value. So the x at this point is important. We'll find the other point on the unit circle with the same x, and then we'll go ahead and draw the same blue line, but down to here. By symmetry, this part is also the 1.4, which means that the real angle that I want is going to be 2 pi minus the 1.4. So we'll do 2 pi minus the answer. So that's our other fundamental solution. Okay, so at this moment, we're going to add our 2 pi k's onto both. Have to do it here, not after you solve for the variable. And then finally at the end, we solve for t. So we're going to multiply both sides by 6 over pi. Okay, so let's go ahead and do the calculations here. So we're multiplying this guy by 6 divided by pi. That's fine, and then we'll go ahead and retype a bunch of the decimals. I'm doing this right, 42744. Okay, that's fine, and then multiply by 6 over pi. And apparently we didn't do it fine. What did we do wrong? 6 divided by pi. Okay, so we get this. Unfortunately, I've lost my other answer, so I got to type some stuff again. 4 point divided by, nope, times 6 divided by pi. Okay, so if I've done it right, then these are our two new numbers after we solve for t. So let's go ahead and write our answers down here. So this guy becomes t equals, so this was the 1.4, that's the first one, 2.726 plus, I'll leave that blank for just a second, and then this one becomes t equals bottom one, 9.27 plus. Okay, but remember we're multiplying the whole equation by 6 over pi, so that means this guy also gets multiplied by 6 over pi. So if you can do that in your head, the pi's will cancel and the 6 and the 2 will multiply and we'll get 12k. And 12k actually feels really good to me because that's just saying add a bunch of 12s as many times as you want, and that's quite a reasonable thing in this problem because if you're sitting at a particular point, for example, if you're sitting at this point right here, the first solution, and you add 12 minutes, well, that's going to land you exactly on the same point, but one cycle away. And then if you add another 12 minutes, that will land you on the next one. So that makes perfect sense. We found the one solution, and then we're just going to add a bunch of 12s to get the other corresponding ones. And then the same thing for the other solution. Adding 12 will land you on, nope, that wasn't the other solution, that's the same. But this one, who's on the downhill, add 12, you get the next downhill one, add 12, you get the next one. Okay, so how do we use this to actually answer the problem? Well, I don't have any space here, but maybe I can squeeze it in on the side. I'm just going to make a little chart that's going to have values of k. And then how about I call this T1 and T2, just so I don't have to write them all again. T1 and T2. Okay, so if we plug in, for example, k equals 0, then T1 just becomes the 2.7 and change. So these are minutes. How about we just round to the nearest tenth of a minute? That's fine. And T2, if you plug in k equals 0, right here, this term goes away. And so we'll just get this 9.3. And so those are the first two answers, 2.7 minutes in and 9.3 minutes in. are the first two times that we reach a pressure of exactly 150. And then we'll go ahead and plug in k equals 1 and k equals 2 and 3, and I think 4 will be the last one. Okay, but I'm kind of lazy, so I want to use my calculator to do some of this grunt work. So here's how we do it. I'm going to go in actually and type into the y1 these two things right here, 2.7262 plus 12x. And then down here, the other one, 9.2737 plus 12x. And then I'm going to go into second table set. And I'm going to change the starting value here to 0. That's like the k equals 0. This delta table says go up by 1 every time, which is what I want the k's to do. And then down here, I'll change this to automatic. Yours is probably already on automatic. And then if I have that table set up looking like that, then hit second table, and we will have our answers. When k, it's not x, it's k in this case, is 0, we get 2.7 and 9.3. That's what we wrote. And the rest of these numbers are the next few answers. So that's a real fancy way to use your calculator. The easy way in this case is to recognize that we're just adding 12s to each of these numbers. So 2.7 becomes 14.7, becomes 26.7. That's these next few. And we just keep going until we get past the first hour, and past the first hour happens right there when you're plugging in 5. That's at 62 minutes. It's too far. So 4 is the last number that we need to write in. Okay, so out of sheer laziness, I just took a screenshot of that calculator instead of writing down all the numbers, but there they are. Those are the times during the first hour when the pressure is exactly 150. Okay, number 3, last class, we saw the basic approach to solving trig equations. I won't read it, but if you need to refresh your memory, you can pause the video and read it now. Number 4, sometimes isolating the trig function takes some work. Find all solutions to each of these equations. So let's start in part A. 4 cosine of t plus 3 equals 9 cosine t. So for the first time, we now have 2 trig functions in the problem. We need to make it so there's only one trig function in the problem. So let's go ahead and move the cosines from the left over to the right. And we'll do that by subtracting 4 cosine t from both sides. And these are like terms on the right-hand side. So the 9 subtract the 4 just gives you 5 of the thing. The thing is cosine t. And now this looks a whole lot more familiar. Isolate the single appearance of the trig function now by dividing by 5. And then what are we trying to do here? All solutions. Okay, so then we'll do inverse cosine of both sides. I'm just going to swap the two sides of the equation so it looks more standard to us. And then we'll get our 2 fundamental solutions. First one from the calculator. So we're doing inverse cosine of 3/5. So we get that. Okay, we'll go one more. And then we need the other answer, and so our quick unit circle will help us find the other answer. So 0.927 is in the first quadrant. Hopefully you see why. And this is a cosine problem, so we need the same x value that we had here. So we'll go straight down and find this point. Same blue line, so the same 0.9, and then the standard version of the angle that we want is there, which is going to be 2 pi minus. So we do 2 pi minus the answer. So 5.355. And so that comes over here as our second fundamental angle. So actually, I guess it rounds up to a 9. Details. Okay, I think that's right. And then we're pretty much done. Just stick on our plus 2 pi k. Nothing else to do here because it's just t by itself. So those are our answers. One thing I forgot to mention when we had this previous problem about the pressure done is that now that we've got our answers from the table over there, what you might do if you want is go ahead and retype this equation into your y1 and then get a real nice picture in front of you. So use this window right here and then go ahead and graph y2 equals 150 to get that horizontal line, and then use the intersect command until you are tired of using it, and just go ahead and confirm that the calculator gives you the numbers that we have as our answers in that table. Okay, next page. B, tan t equals 7 over tan t. Again, trig functions appearing in multiple places. That's no good. We need to get the trig functions to be on the same side. So how about we multiply both sides by tan t for the purposes of getting the trig function out of the bottom over here and moving it to the right-hand side. So that means that we have tan of t squared is equal to 7. I'll just say that mathematicians would not have written it that way. They would have written it as tan squared t equals 7. They mean exactly the same thing. The virtue of writing it the second way is that you get to write 2 fewer symbols. You don't need to write those parentheses. But we'll write it this way. And then we're trying to solve for the trig function, isolate that trig function. So how about we take the square root of both sides? And then the square root on the left-hand side cancels with the square, so we just get tan t equals square root of 7. Super. And then we can take inverse tan of both sides. If you're on the ball, you'll realize I've made a mistake, an error of omission, but we'll just proceed merrily along and then we'll come back to that error. So inverse tan of 7 is good. Again, we got to find the 2 different answers, so use the calculator to find the first one. One quick thing, inverse tan of, just type in root 7 first. So root 7 is about 2.6. So if I wanted to do inverse sine of 2.6, we actually tried that in the previous class, or I guess it was in the activity, the last problem in the previous activity, where we had to find inverse sine of something like negative 2.5, and we got an error. And we said, oh yeah, you can't plug in 2.5 into the inverse sine function. Inverse sine only accepts as inputs numbers between -1 and 1. So this number is no good for inverse sine. It's also no good for inverse cosine. We're trying to plug it into inverse tangent. So is 2.64 okay to go in to the inverse tangent function? I don't know. Let's see. Inverse tan of second answer. Oh, apparently it's okay. So if you need to, go back to our little chart from a few classes ago where we looked at the domain of each of the inverse trig functions. And you'll see that for the inverse tangent function, the domain wasn't -1 to 1, like it was for inverse sine and inverse cosine, but it was actually -infinity to infinity. You can plug inverse tan of anything, and you'll get a perfectly good number. So there's our first answer, 1.209. Okay, that's fine. That's one fundamental answer. We need to find the other fundamental answer. And we do that with our old friend, the unit circle. So 1.209, it's in the first quadrant. This is inverse tan. Okay, it's not just x and it's not just y, but actually we know that the tangent of something is y divided by x. So we need the y and the x to be the same numbers, but we need the, I don't know how to say this best. If the fraction is positive, which in this case it's a positive, what was it, 2.6, then we need to find another place where y over x is going to be a positive number. So at this particular point, x and y are positive, and apparently the ratio of those two numbers is 2.64 at this special point right here. But if you were to try to drop down here, you would find that the x is a positive number, but the y is negative. And when I divide those two, I would get a negative 2.64. And if I tried going over here, I would say, oh, okay, here the x is negative, but the y is positive. That doesn't look good. And if you divide those, you would get, again, negative 2.64. So there's only one other point that has a chance. Let's try this one. Here, the x is negative and the y is also negative. And when I divide those two negative numbers, I'll get a positive number. And so the answer that we want is actually the one that's symmetric, going right through the origin. And so using the symmetry, there's the 1.2 right there. And so then the standard version of this angle must be here to here, which is pi plus the 1.2. Okay, so that's our other answer, 4.3510, or 4.351. Great. And then we stick on the plus 2 pi k's, and we're done with this problem, kind of. Okay, so first a small issue and then a bigger issue. So the small issue, these answers are fine. I mean, these are correct answers to the original equation. The small issue is that we actually could have compressed those things together, because the fact is that if you're standing on this one angle right here and you want to land on that same angle again, you can zip all the way around to the 1 revolution mark and then go to the top, and that's fine. And that represents the first this first equation down here. Let's just go 1.209 after as many revolutions as you want. Or you could say, okay, I actually want to go to the second one, so how about I go around 1 complete time and then I'll go around another, whatever it is, 4.35 radians, and that's fine. But it turns out you can actually merge these two things together. These two equations that we've got here, you can merge them into one, because you can say, all right, how about we just go to the first equation, the first solution, I should say, 1.2. And how about from there, instead of zipping all the way around the circle back to that same angle, what if we just try to zip to this guy? How far do you have to go from here around to here? How many radians is that? Well, that's pi radians. That's half a revolution. So you can get from the first answer to the second answer by going half a revolution around. How could you go from the second answer back to the first answer? Well, that's just another half a revolution. And so the fact is, you can just merge these two things together into one solution. I'm going to write this, then I'm going to erase it so it's not confusing. Or you could just say, hey, how about we do 1.209? We'll just pick that one. And then instead of saying zip around pi's, zip around 2 pi's, which are complete revolutions, let's just zip around by pi. And in doing that, we would say that these two solutions right here are equivalent to this one solution. And mathematicians often like efficiency, so why not write just the one equation instead of the other? Well, I'll tell you why I don't teach it that way, is because I don't want to teach something different for tangent than for sine and cosine. The things that work for sine and cosine are this and only this. It happens that that this thing also works for tangent, so why not just use that for tangent? Well, you could be slightly more efficient if you want to, and just do the plus pi k, but then you're doing something different for tangent as you are for sine and cosine. So that's just kind of a philosophical slant on why I would encourage you just to do the plus 2 pi k's every time, but completely your call. This right here is a full credit answer. It's also pretty clear if you think about the period of tangent, it's not 2 pi. The period of tangent is pi. Tangent repeats every pi. So if you are standing on a one branch of that tangent function, then you can get to that same point on the next branch by just adding pi. And so in some sense, adding 2 pi for tangent is not the natural thing to do. Adding pi is the natural thing. Okay, so I said there were two issues. That was the small one. The big one is we're missing some answers. In fact, we're missing infinitely many answers. And the problem was in Algebra 1. When I took the square root of both sides of this equation, I forgot to do something fundamental. When you take the square root of both sides of an equation, you got to put in plus or minus. Okay, so we've got our perfectly good answers here for the positive square root of 7, but what we're missing are the answers for the negative square root of 7. So we need to do inverse tan of negative square root 7. I expect we're going to get a number that looks quite similar to numbers that we've seen before. Okay, the answer here is negative 1.2 instead of positive 1.2. Okay, not surprised, but we got to include that. So the other answers that we're going to get, I'll do this over here in purple. T equals inverse tan of negative root 7. So we get negative 1.209. And then we got to get the other fundamental solution. And then we'll add our 2 pi k's and we'll be done. So quick unit circle drawing here. Negative 1.2 is in the 4th quadrant. We're looking for the same point, but on the opposite side of the circle. Every time you have tangent, turns out the other winner is on the opposite side of the circle. So this is also a 1.2 here. We'll just call it positive. So that means that the standard version must be pi minus that number. Okay, so we get about 1.39, 1.93, I should say. Okay, so that's good. We'll stick on our 2 pi k's and be slightly less efficient than if we just written one of these equations with a plus pi k. But that's okay. We got it right. So we've got those 2 answers there, these 2 answers over here, and that's the complete collection of answers to the original equation. Okay, moving on to C. 1 minus 5 sine x equals 3 cosine squared x. Goodness, that equation is worse than any that we've seen so far. Okay, so not only do we have 2 trig functions appearing, we actually have 2 different trig functions appearing. Furthermore, one of them is squared. And I mean, I guess we handled the tangent squared up above, but this just feels different. There's a cosine being squared and then a sine by itself. Okay, so what we need to do is somehow get it so that we have only one trig equation. So we need the same trig equation to appear. Sorry, the same trig function to appear. This whole solve the equation with sine and cosine in it is for the birds. So we got to do something to get rid of one of these trig functions and replace it with the other one. Okay, so there is an identity that we know of, a real famous identity, that relates sine and cosine to each other. And that identity was the Pythagorean identity. So the fact is, sine squared x plus cosine squared x is always, always, always 1, no matter what x is. So how about we solve this equation for cosine squared for the purposes of replacing this cosine squared with something else. So subtract sine squared from both sides. Might be tempted to take a square root of both sides at this moment. Don't. We're ready to replace. Cosine squared right there can become 1 minus sine squared. So this equation now becomes, copying the left-hand side, copying the 3, and then cosine squared becomes 1 minus sine squared. Okay, what have I forgotten to include? Parentheses. That cosine squared was one thing. It's still one thing, so it needs parentheses. And this is feeling better. I still don't quite know how to solve it, but at least it's only got sine and not both trig functions in it. Okay, so let's distribute on the right-hand side and start cleaning this thing up and see if anything good happens. Okay, well this one has a squared term in it and a non-squared term. It's got sine squared and it's got sine. How about we get 0 on one side of the equation, just bring everything to the left. So add the 3 sine squared, copy the minus 5 sine x, and then subtract the 3 from both sides. So I think I've done that right. And if we kind of do a little substitution in our minds, this sure looks an awful lot like something of the form 3y squared minus 5y minus 2 equals 0. So I don't know the exact technical term for this kind of thing. I think it's the original equation here is set to be in quadratic form. So maybe that's a phrase you've seen before. Some folks really like to write out the substitution. If you can factor this thing without the substitution step down here, go for it. I like to do the substitution and then factor and then go back. So I guess I'll say here where y is what we were thinking of as sine of x, which is kind of a funny equation because normally, no, that's fine. Okay, so quadratic formula, if it doesn't factor, I'm guessing this one does factor. So let's see what we can do here. 3y and y. We need to get -2, so how about like a -2 there and a +1 here. So with some trial and error, or maybe you've got some other technique, like there's the box method of factoring. There's funky factoring, if you've heard of that. So lots of different ways you can get it. I think this is the correct factorization. So what that means is that 3y plus 1 is 0, or y minus 2 is 0. Solve both equations separately. We get y is -1/3, or y is 2. But y is something that we invented, so let's go back to black and change the y's back to sine of x's. Okay, two ordinary simple looking trig equations for us to solve after we did a lot of other work to get there. Okay, before we go any further, one of these equations is kind of funny and should look funny to you. Which one is it? It's the sine x equals 2. This one here has no solutions because 2 is too big. But the other one has plenty of solutions, so let's focus on that one. We'll go ahead and do inverse sine of both sides. X equals, we'll get our first fundamental solution on the calculator. Okay, so we're doing inverse sine of -1/3. And we get that angle. So that's our first one. Let's call that -0.34. How about that? And then a quick unit circle will give us the other one by symmetry. Okay, -0.34 is in the fourth quadrant. Not to scale. This is a sine problem, so it's the y value that's important. So we grab the angle that has the same y value. It's over here. And then by symmetry, this angle in here must also be 0.34, which means that the standard version of this angle must be pi plus 0.34. Okay, so we'll use the calculator here. So what are we doing? Second pi plus the 0.34, so we get 3.48. Did we do that right? I think that looks good. Okay, so we'll grab that, put it here as well. We've got our two fundamental answers. All we have left to do is stick on the plus 2 pi k in both. And we're done. And we haven't really done this before. I mentioned that you could have done it with the pressure example, but how about we just spend a minute here graphing the original equation and seeing if the calculator agrees with the answers that we got. So we're going to graph y1 as the left-hand side. 1 minus 5 sine of x. And then y2 is the right-hand side. 3 cosine x. And to type it in squared, you got to do something like this. You might put extra parentheses to be really clear, but I think this will take care of it. Okay, let's think about the window. What are we doing here? So how about we go from 0 to, say, 2 pi. And we can go by ones. And then for the y's, I don't really know what's going on. I know that cosine normally goes -1 to 1. So this will go -3 to 3, but this will go -5 to 5. And that 1 might jog things a little bit. So how about we go -6 to 6? And we can go by ones there. So make sure you're in radian mode. And if we've done things right, then we should see a good looking graph. So there's the 1 minus 5 sine. Okay, haven't seen that behavior before, but that's apparently 3 cosine squared, and we see 2 points of intersection. Second calc, 5, enter, enter, enter. And we should get the first point, well for me, anyway, I get that 3.48. That sounds familiar. Oh good, 3.48 is right there. The other answer I got is negative 0.34. Now that is not going to show up here. But let's go ahead and find this number real quick. Second calc, 5, enter, enter, and then you just need to get the cursor to go to the right. So you can just hit the right button a million times, or if you want to be quick about it, you just type a number that's close to the answer. This is a 6 right here, so I'm just going to type 6. And I get this guy, so 5.94. Well, remember we had said down here that our answers were negative 0.34 plus 2 pi k. So how about we come out here? I'm just going to clear the screen and hit X because it still remembers the answer we just got. And I'm just going to type in negative 0.34 plus a single 2 pi. Fingers crossed. Oh, hooray. Rounding errors here because it wasn't really 0.34. There were more digits I could have written down. So you can always solve the trig equation and then check your answer using the calculator. Okay, number 5. The rabbit's activity that follows reviews sinusoidal functions and looks at finding solutions to a trig equation. Give it a decent shot before you go look for the video for the activity.